Hi, everybody. Thank you for joining the Synthetic Intelligence Forum online. My name is Vic Pant. I'm your host. And today I'm very excited to bring a friend of mine to the Synthetic Intelligence Forum to talk about a very exciting topic, which is genetic algorithms. And specifically, Aymeric will talk about the notion of optimization, adaptation, and learning with genetic algorithms. Aymeric is a friend of mine, and he is a subject matter expert on this field. He's joining us from the University of Oxford. And Aymeric and I often joke about genetic algorithms being a substitute for running down hills with gradient vectors for slopes. And then as we were talking, actually, if it's a reinforcement learning problem where the goal is not to minimize a loss, but to maximize some sort of a return, then certainly it's running up hills with the gradient vectors for slopes. So without further ado, Aymeric, I'd like to welcome you to the Synthetic Intelligence Forum, and I'd like to invite you to take it away. Thank you.
Thank you very much, Vic. Thank you, everyone who joined. I'm extremely honored to be here and very happy to share with you maybe some exciting things about this new technique, genetic algorithms, and hopefully present to you some very exciting projects and applications, and hopefully some new perspectives for the field. So I hope that I will be able to convey the passion and the potential that these methods carry. Today, I would like to first briefly explain what a genetic algorithm is. I will be often saying GA for genetic algorithm, but I will try to give you a full picture of what are the main concepts behind it, what are the main steps of the algorithm, what are the main parameters involved. And I'm going to try to present this with you we're using a very simple example, so you can actually see a very simple GA running in order to really understand what's going on. And this will open to describing the qualities and the challenges of these methods. So as a search algorithm, it has some potential, some nice things, has some desirable qualities, but it has also some limitations, so some things that are challenging. I will try to describe them. Then, as a fourth section, I am going to talk to you about some exciting applications and projects. I'm not going to spoil you, but you can expect to see some real-world problems trying to be tackled with this method. And finally, I will try to mention some work that is currently under development, some work that is in progress, and some maybe perspectives for the field. There's been much progress on this technique. GAs actually on their own have been there since the 70s, the 80s. They have been quite popular at that time, and they have been steadily increasing in use across many different disciplines, across many applications, especially for operational purposes. And some very recent developments we're talking about things in 2018, 19, have really, I think, shed new light on what GAs could do, or what GAs could become. And I'll try to give an overview of that. So what is a genetic algorithm, or a GA? It is a search algorithm. So an algorithm that is searching through a space of possible solution in order to find the best solution to a given problem, or the best solution in a given environment, that has two main characteristics. The first is that it is population-based. Whereas in many different search algorithms, I'm thinking about reinforcement learning, you would have a single agent optimizing a reward function in a given search space. In the genetic algorithm, you're really evolving a population of solutions. You will never be restricted to a single individual. You're going to deploy many different individuals in different points of this search space, and you're going to try to look over the search space for promising regions and promising solutions. The second big characteristic is that they are adaptive. That is, the core engine behind genetic algorithms and behind this search process is actually an attempt to simulate Darwinian evolution. So your solutions are somehow going to be considered as organisms that have some genes, they have some characteristics. You would really see them as some digital organisms, some individuals that are going to be subject to the laws of evolution. And to implement this optimization by the means of evolution, the basic principle would be that the fittest solutions, the fittest individuals in our population are going to reproduce, they're going to be more likely to spread their genes in the next population, in the next generation of individuals. And the bad ones, those who don't score well, who are not very adapted to their environment, are going to be, will tend to be discarded in this selection process. So by simulating this Darwinian evolution with the hidden belief that if evolution created all life on Earth and our intelligence and our brains and everything that we know, it must be a powerful mechanism, and there is a way to harness the power of this evolution mechanism into our algorithms to have a new, different search method. So different key steps of this evolution will be mentioned, and the core steps of the GA will actually mimic these key concepts. I'm talking a lot about selection, reproduction, crossover or recombination of genes. Crossover is really one basic way by which two different individuals in the population are going to exchange their genes, and that the children solution of these two parent solutions are going to incorporate some elements of these parents. And a key last element would be mutation. And I'm sure you're very familiar with the idea of mutation, but it's going to be these small exploration steps around the search space. So to really build on this idea that we are actually applying evolution to a search for a solution to a given problem, you can see it really as an analog of an instance of natural evolution. If our objective is to create a very perfect giraffe that is able to survive in its environment, and if the environment is characterized by having very tall trees, then a natural result of evolution would be a tendency in the population of giraffes to move from a balanced, maybe average height to a higher height. And the way it is going to happen is that the individuals who have a too smaller neck would not be able to feed themselves, and they are going to die and then not be able to reproduce. And eventually, you're going to have only a population of tall giraffes. And the same intuition will hold for how GAs work. You're going to define a performance measure, a fitness measure, that is actually analog to a reward function or loss function. And you are going to say that the individuals that have very high values of this fitness, that have longer necks in given environment, for instance, or that satisfy the requirements of the given problem, are going to be more likely to be selected to reproduce themselves and to spread their genes. So how do they work? So here I'm really going to go through the main steps, and I'm going to show these main steps with a very simple example that is quite familiar for those of you who already done GAs before. This is the counting ones problem. And here in this problem, we are just starting with a vector of 0 and 1s. So each row here is a vector of 0 and 1s for a given length. And you have a lot of these vectors. This full matrix in which each row is an individual, this matrix is our population. So we here have a population of 3 and others, individuals, and each individual has a sort of DNA. This line, this road, the alternance of 0 and 1s, is the DNA of this individual. This is the genetic representation of this individual in the program. And our goal in the counting ones problem is actually to start from a random population in which you can have any combination of 0 and 1s to a full vector of 1s. This is a bit artificial. This is just an illustration, but you could imagine that we are dealing here with some kind of system in which if I have all the 1s, it means that I have a very tall neck, I'm a very tall giraffe, I can easily feed myself. And if I only have 0s, well, I'm very, very small and I'm not going to be able to feed myself. So obviously, the path to better fitness is the path to obtaining as many 1s as I can in my DNA. So the first step when you're trying to apply a GA to something is to have a problem first. They really wouldn't work if you don't know what you want to achieve, if you don't know what you're doing. So here, the problem that is selected is a simple one for illustration. This is the counting ones problem. The second thing you're going to define is how are you going to represent the solutions to this problem? How are you going to represent the search space, that is the space of possible solutions? And you have this step in many different algorithms, but the genetic algorithm has a very special feature, a unique feature, which is that it really puts an emphasis on having a genetic representation. It's just not a function. It's just not a parameter. You really want to put as much genetics as you can into the equation to really have this genetic evolution drive coming in. So there are infinitely many different ways to represent a solution. Our DNA itself is made of 4, we illustrate it as being composed of 4 letters, A, C, T, G. In the previous example, the counting ones, I mentioned vectors of 0 and 1s. This is known as a binary string or a bit string. You can imagine any possible representation. You just have to be consistent with the problem you're studying and the operators, the next steps that are going to be implemented. So here we have our problem. We want a vector only composed of ones. We have our representation. All individuals are characterized by a vector, and this vector is a binary string of 0 or 1s with some length. This is just the number of elements in your vector, in your genetic representation. So this is our starting point. What do we need then? Then we need to create a population. We are in the first stage of the algorithm, and we need to start somewhere in the search process. So usually we are going to create a population of solutions. We will decide an arbitrary size. Let's say we can build 100 of these individuals, and we are going to create them randomly. And we're going to start with this population, this initial population of 100 individuals that have this genetic representation, and each one may or may not be different. And hopefully, by iterating the steps of our GA, we'll be able to start from this very random, very imperfect population to great solutions to our problem of counting ones. So the first step, now I'm entering into the evolution loop. I'm entering into the loop that's going to be repeated a certain number of times. This is really the evolution process. The first step in this evolution process is to evaluate each individual of your population. You have this big population, everyone has a given genome, a given DNA, and you want to evaluate these individuals. You want to give each individual a score, and this score here will be called a fitness. So typically, the way it's done is that you're going to define a fitness function that allows you to reach your objective. That is, if you maximize or minimize your fitness function, depending on your problem, this is going to be a good way to converge to your objective. So here in the counting ones problem, one very simple way to do it is just to say that the value of the fitness of each individual is equal to the number of ones in its DNA. That is, if you have a length 100, if the chromosomes are, the genetic representation is 100 elements long, then if you have 100, it means that you have ones everywhere, so you have maximized the fitness, and you've essentially solved the problem. If you have not a single one in your function, this f will give you a score of 0, which illustrates perfectly that you're not fit at all. You're not really solving the problem. So this way of evaluating fitness by setting a fitness measure by the form of a fitness function is really something that is frequent. And here, if we take this example of a population, we have 3 individuals. The length is equal to 3. The first individual has 1, 1. The second has a couple of ones. And the third one has none. So if you apply this fitness function, you count basically the number of ones in each individual. And the first one has a score of 1. The second has a score of 2. And the third has a score of 0. So essentially, the fitness will tell you how much are these individuals solving our problem, how fit are they to the environment. So now that you have evaluating all these individuals in the population, you're going to try to have some selection. You're going to really to model the reproduction process. So in nature, all these individuals would have very specific characteristics. Maybe some would look stronger, maybe some would look more fit, some would be more attractive. Here we really reduce all these dimensions of attractiveness and mating choices to the fitness values. And here the fitness values are going to help us decide what individuals deserve to be the parents for the next generation. What are the best parents to get the best next generation? And there is many different ways you can do it. One way is to use a rank selection. That is, you're going to pick a given number of individuals, you're going to evaluate them, you're going to rank them. So here, this will be our best individual. This is the second one, this is the last one. And you will say, I'm selecting the first K individuals. And these K individuals are going to be my parents. So here, if we had a selection of rank 2, we would be picking essentially our 2 best solutions. And we will be picking the 2 first. One other way is to use fitness or different measures of fitness. And you could say that one individual probability of being selected as a parent could be equal to the relative fitness of this individual over the full population. So here the full fitness would be 3, and this individual would have 1/3 of probability to be selected, and this one 2/3. And you would repeat this draw over and over many times. The idea is this selection step is that there is a lot of way you can do it. There is a lot of way you can tune your selections toward being more aggressive or less aggressive, depending on what your problem requires. But the key, the core idea is that you are going to be selecting the best individuals to create the next generation. So this is the descent with modification step that is very familiar in the biological literature on how Darwin initially described evolution. And this is actually the core mechanism of the GA, because this is exactly where our good genes, the good results of our search process, are going to be conserved and amplified in the next generation. We have a different succession of generations, of populations, each at a different time. And each population aims at maximizing the fitness. You have to understand it based on the selection process, the evolution function, the evolution process. And the transmission of the good genes is essential between generations, so that the next generation is at least as good as solving the problem, but maybe can be even better in solving the problem. So one way this is done, one way this inheritance mechanism is done in GAs is called the crossover, which directly inspires from the way DNA DNA sequences can melt and recombine in the meiosis. So this whole mechanism will happen with a given probability, but the key thing is that the crossover will basically align the two sequences, the two DNAs. So here we have our two parents, and the crossover will essentially choose a point, a crossover point, at any location of this sequence. It could be here, it could be here, it could be here, it could be here. It's all random. This is called the uniform crossover, although, of course, you have different variants of crossover. But for here, we just have a uniform random crossover. So we're just going to slice our sequences. And we have just decided to slice them here. And what happens is that you're going to intertwine the sequences. That is, you have this first individual that is blue, the second that is white, and the parents of this reproduction between these two parents is going to be an individual composed of the blue sequence up to the crossover point, and then the white sequence after the crossover point. And the exact reverse will go on for the second individual. So the second individual, we have this element of the parent number 2, the white one, before the crossover point, and afterwards is going to have the sequence, the DNA, the remaining part of the DNA of the parent blue as the remaining part of its sequence. And essentially, this is going to be some large exploratory leaps. It's going to be a large exploration jumps in the search space, as individuals will be potentially able to exchange big sequences of DNA. Essentially, if you see all these different individuals as in specific locations of the search space, this crossover step allows you to make bridges in this search space between very distant points, potentially. This is the large exploration part. One very important mechanism in evolution, and we are seeing it on a daily basis with viruses as well, is the mutation step. That is, when we have this DNA copy, this DNA recombination in nature, the process is not perfect. There are various ways the chromosome, the DNA can be damaged. You would think about UVs, for instance. The UVs can damage our DNA, can damage the way our DNA is multiplying in our cells. And any other possible mechanism can actually have such an impact. And what we said here is that once we have crossed our parents and we have our two children, we said that some elements of their DNAs may mutate. They may encounter any error. And in our case, with the binary string representation, a 0 might become a 1, a 1 might become a 0, and this can happen to any element independently. One parameter that would govern the amplitude of this mechanism would be the mutation probability. A number between 0 and 1. If you have low mutation probabilities, there are low chances that any element will mutate. If you have a high one, chances are greater. I want to attract your attention that here, we specify mutation as one. This is extremely specific first to our genetic representation, choosing a bit string, and also specific to our problem. There are, I think, dozens of different mutations or mechanisms that have been used in GAs, and the right one is probably indefinite. You can use different ones for the same problem. They won't have the same impact, but it's just to show that not to too much overfitting this example. So here, what happens in this instance is that we had these children, not perfect yet, that have emerged from the crossover step, and by accident, this second individual has undertaken a mutation on his third gene of his DNA, and his 0 has become 1. So this is just the sense of the mutation step. When in the crossover step we had large jumps in the search space, this mutation step is more like smaller jumps, just marginal improvements. I'm in a very specific region of my search space, and I'm just going to do one step at left, one step on the right, and that's it. Essentially, the mutation operation is going to help your GA not get stuck. It's going to help you to maintain some continuous level of diversity, some continuous level of search. And this is going to be very important in preventing your program to be stuck on some local optima. So once we have all these steps, we have obtained 2 children for our 2 parents, and we're going to be iterating this reproduction and mutation step as many times as it takes to obtain the next population. That is, until we have enough children to fill an entirely new population of the same size. And we are just going to iterate this big loop of evaluation, selection, reproduction, mutation, either until we find a solution for our problem, when we know the solution in advance, or for a given number of iterations or time periods. This is an example of what happens when you run this counting once problem in a GA. The code is actually extracted from a book that I'm citing later on. It's called Hands-on Genetic Algorithms with Python. It's an excellent book that comes with GitHub codes available. There is a reference later. But if you run this code and you said that in our counting one problems, the DNA strings are of length 100, so we are aiming towards 100 ones consecutively. And if we run this evolution process for 100 time periods, this is the progress curve that we can observe. So there are other parameters at play. I'm not going into much detail over there, but this is interesting to see that with such simplistic steps, and it looks simple, it is simple, it looks basic, but it's still surprisingly efficient. And you can see in this, it is that between the score 0, in which we have very bad vector, everything is 0, and 100, in which everything is 1, from a random population, we actually converge pretty quickly to a good result. I haven't run the program afterwards, but you would typically expect the solution to be found around iteration 120 or something. You can see the maximum fitness of the individual in the population, that is the score, the fitness of the best individual at each step, and the average of the fitness of the population. And you can really see these good individuals, these lucky draws of mutations, or these well-made crossovers between good individuals. You just put 2 good individuals and you find out that if you combine them, you can obtain something even better. This really drives the population towards progress. And you can essentially solve your counting one problems with such simple, basic steps. In an environment in which it would take longer, much longer, to actually find this perfect vector by exhaustive search, because you would have so many combinations to check that you would need much more than 1.5 seconds to solve the problem. This was a very simple problem. This is just finding one scene vector, and many different methods could do it. So why makes GAs interesting? Why should I be even attending this talk? What should I be thinking about GAs to solve any problem? And this is really what I'm going to try to describe now. And if you want really more details on that specific aspect of qualities and challenges, a lot of information exists on this, and all the GA papers will at some point mention the strengths and weaknesses of the technique. But what I found getting involved in the field was that all this information was really scattered. And it was really hard to get a comprehensive, condensed compendium of all of these key facts and all this knowledge. And especially that you had some textbooks on GAs, and they were maybe somehow a bit old. So what I really tried with this article was to try to put a recent overview with recent applications and recent knowledge, recent research, to revisit what the qualities and challenges are. And in the next slides, I'm going to give you a very short summary of this article. So what are the qualities of this method? The first quality is that they are actually very good at exploring very large search spaces. So search spaces are, of course, the space of possible solutions. And when these spaces are very large, we're talking about the order of 10 point power 60, 50, 60. This is extremely large spaces. When they are very complex, when they have very complex structures, when it's not just well-behaved or just a very nice concave curve. Now, when it's really ugly, when it's just like a mountain chain, when it has a lot of dimensions, this is where GAs can be surprisingly efficient because of this population-based search and this ability to make big jumps and smaller jumps in the space, thanks to the operators. They achieve some near optimal exploration or exploitation balance. There are many ways to tune it. You can adjust your parameter and your operators to have more exploration or more exploitation, depending on what your problem requires to be solved. But essentially, this is a very flexible method that will try to balance these two conflicting aspects. In these very large, complex, or high-dimensional search spaces, GAs are actually quite fast at locating promising regions. They are not so fast to identify the exact optimum. I will go back on that. They have also some very nice guarantees of convergence. In the standard GAs, you have some mathematical analysis, some theory of evolutionary computation that shows that these GAs will eventually converge to the exact optima. And finally, this is a method that you can use when you don't really have so much information or understanding on your problem. This is extremely nice when you're looking for a solution to a given problem and you don't even know what the solution is going to look like. Like what's the best financial strategy? What's the best strategy in this very specific game? What's the best way to solve global hunger? You don't really know what the solution is going to look like. And you want a method that will work with few assumptions on how this solution is going to be looking like. And these GAs, if you give them a flexible enough genetic representation, can actually work with very limited information and give you a more unbiased solution. It's not strictly unbiased because you just assume that you can get a solution to a problem based on a very simple limitation of nature, but this is still a good way to handle problems that you don't really understand fully. And a final key point that has been quite popular, especially in some parts of economics, has been that you can actually model learning and adaptation with these GAs. You can say that the crossover step is just two individuals that are communicating. Let's say you're just playing a game, and the analog of crossover would be two individuals meeting and discussing, oh, okay, this is my strategy in this game. I'm doing this and this and this, and say, oh, cool, but I'm doing that. And the result of this communication will be some exchanges, and the two players may incorporate a part of the other strategy into their own. And the mutation step will be just some small personal experimentation. Like I'm playing this game of chess, and I have this usual pattern. And what if I change just this specific period? This is really the analog of our mutation step. So we have all these qualities. This is really nice. So where is the trap? The trap is that the challenges are that first it comes at a cost, and the cost is computational. You have a very high scaling of the computational complexity of these algorithms with the population size. So if you have a very large population size, your algorithm is going to be increasingly and exponentially slower. We have this evaluation step in which we just apply our fitness criteria, our fitness function to all the individuals in the population. And sometimes the fitness evaluation can be quite costly. It can take some time to evaluate all the individuals, and especially more if your program is challenging, if the fitness is just itself in a simulation, or if you have many individuals to evaluate. There are some ways, some operators, some parameters you can play with to try to reduce this cost, but this has remained a big challenge over the next 4 decades in GAs. One other key challenge has been parameter configuration. I tried to show you a few of them in green. These are the most basic parameters, but you have population size, mutation probability, crossover probability, the genetic representation. This is a very tricky problem to solve because you have many parameters. They will have some impact on performance, and it's actually non-trivial to find how different combinations of parameters may create different results in terms of performance, of convergence speed. Some parameter configurations may even not allow you to reach the solution to your problem. So this is an actual problem, and people have been trying to get their hands on this problem for decades. The last, not the last one, there are many problems there, but one particularly challenging way is also, you remember when we said first we select our problem and second we choose our genetic representation. The problem is this choice is really not neutral, and this choice is really going to impact your search. You are, by adopting a specific genetic representation, you are really setting bounds on the search. You're saying, okay, I'm looking at all the different combinations that are with these genetic representations, all the combinations of 0 and 1s over a left 100, but you're not looking at everything else. You're just looking at this representation. You're really constraining your search. And this can be fine for many things. I mean, if you are just counting once, you don't need the 0-1 representation is fine. But if you're looking for, let's say, the best financial strategy, what is the representation of the solution? What is the best representation? And you really want to be sure that your representation can cover the full, can span the full search space. You don't want it to just look for a very limited subset of the space. And you don't want to create an intended bounds to the search. So this is really where this choosing a genetic representation can be very tricky. Similarly, the way you design your fitness function is going to really impact your search. Because if you have a poorly defined fitness function, your program may actually find some loopholes, or you could lead to deception. Deception in search is when following the objective gradient would actually not allow you to reach the objective. And in poorly defined fitness functions, you may have this problem. One other problem relating to computation cost would be that the fitness function could be actually quite costly to compute, especially if you have many individuals to evaluate. And finally, this is both a quality and a challenge, but GAs are described as a robust method or a weak method. That is, they will work well on many different problems, but they will be constantly slower than very specialized search algorithms. And a very good point that was made was that GAs are quite fast at identifying promising regions of the search space, but that they will not locate the exact optimum with the same speed. So they are very good to identify good regions or good possible solutions, but they will still need a lot of time to identify the real exact single optima. And this is actually making more specialized search techniques more efficient and faster when you have some key information when you really have some good information on the structure, on the problem, on the shape of the solution. GAs will not be the fastest method. So having said all this, how are these qualities and challenges used in practical terms? Why do we need these GAs for, and what are the possible uses? The first point that I must really make is that what I'm going to be presenting here is just a very limited experience. And GAs are actually incredibly used because you can find them in computer science, in robotics, in economics, in sociology, in operational research. You can find them in such a wide diversity of grounds, of fields, that it's near impossible to give a complete map of what are the applications of GAs. I tried to cover imperfectly this big word in my review, and here I'm really trying to go over some specific examples. The first example of application of the project, this is really to show you that it looks like a different method, it looks complicated, it looks like it's not fit for the same problems, but it can still solve with our usual problems. And the key thing is that in terms of optimization, they will work around equally well as our usual algorithms. And you have these two examples of functions that are typically thought to be very hard to optimize, the Egelder function, the Himmel-Blau function, that can be quite easily dealt with by a GA. So Wiransky 2020 is the author of the book Hands-on Genetic Algorithms with Python. I really recommend you this book. There is a reference later on. But essentially, he tried to solve the optimization problem of these two optimization problems with very simple codes, and he manages to do it very well. So this was really to show that they look exotic, they look different, but they're also very capable of doing our usual stuff, our usual optimization problems. Some very long-standing applications of GAs have been in game theory, especially when the problems, the games that the agents are playing can be quite complex. Maybe the search spaces are giant. If you consider a prisoner's dilemma, you only have two actions. You can cooperate or you can defect. But if you repeat this dilemma for, let's say, 100 periods, the number of strategies becomes astronomical. And you can have huge search spaces to scan. And exhaustive search method, random search method, we really struggle with this such large search spaces. And a founding application by Axelrod in 1987 was to run the prisoner's dilemma in a GA and observe what the GA would do in this game. And he actually did two things. The first is that he invited many of his friends to submit strategies for the game, and he let the GA train against these expert solutions. And the GA actually found even better solutions. The GA achieved literally superhuman performance in the prisoner's dilemma. And when he ran the GA on its own with a random and much larger training set, he actually got the same result as we have in theory. That is that you have a very good strategy called T for tat, in which you cooperate basically until your opponent defects, and then you defect all the time. This is considered to be a very good strategy at the game. And on its own, the GA rediscovered this. And you have many examples in game theory in which GAs either rediscovered some theoretical results and even extended these results in situations that were not mathematically solvable. Another very exciting application, it's not so recent, but it's really getting better now, is the ability to combine evolutionary algorithms, including genetic algorithms, with deep learning methods. And you have this extremely interesting and I think influential paper, Evolving Neural Networks through Augmenting Topologies, the NEAT algorithm by Kenneth Stanley, that really tries to put these two words together. And the idea will be that the deep learning, the neural network is really good at finding solutions. It's really fast. It's really good at optimizing. But what's the right structure? What is the best number of layers? The best number of the best width, the best parameters, the best sort of activation function. This is not tricky. This is tricky actually. This is not easy to answer. It's very difficult to imagine what is the best architecture for neural network. And these algorithms are just evolving these deep neural network structures by the means of evolution. And their combination just allows some outperformance. There is an illustration of this on a much smaller set, which is that you can actually just take a very basic data set, the Aries data set. So you have basically 3 types of flowers, and they are described by some given characteristics on the petal and the sepal. And you're basically going to try to run a neural network to correctly classify the flowers. But what you will do is that you don't exactly know what's the best number of layers. Do I need 2 layers, 3 layers, 4 layers, 1 layer? Do I need 10 nodes in this layer, 20, 25? Do I need 10 in each layer? Maybe it's 10, 15, 20, 20, 15. I got no idea. So you can use these GAs to actually have a population of neural networks. Each population is going to be evaluated. So each individual is a given network. and it's going to be trained for some time, it's going to be tested, we will get his accuracy and his error rate, and this is going to compose our fitness. So good classifiers are going to receive high fitness, and bad classifiers low fitness. The best classifiers will reproduce, and they will give you possibly even better classifiers. And if you just run this process for 20 iterations, you can observe that from actually completely random structures, so random number of layers, random number of neurons in each layer, you can actually get some pretty good performance. You can get up to 95% of classification. This is not really to set some kind of benchmark in this field. This is a really simple example. This is really to show the potential of this evolution of neural networks and how GAs could be used with other methods so that they can somehow combine their strengths together to achieve new possibilities. There is a new thing, this is completely new because this is my thesis topic, which is with adaptive financial strategies. And this is really a new, different application. It rests on the basis that you can use GAs to model learning. So remember, when you have this crossover, you could say that this is communication and large-scale adaptation. If you have mutations, they will correspond to small learning explorations, some kind of jumps, some kind of perturbations in the strategies. And a big question was, how can we model the evolution of financial strategies? They are very complex objects. When you see the chart of the stock market, how are traders thinking about it? What are they doing? What are they thinking of? What are they looking at? You have an immense diversity of financial strategies as we know them. There is the momentum trading, or also called the trend follower, in which if you observe that the price is increasing, then you're going to see a trend and you're going to buy because you expect the trend to continue. If the price is decreasing, you're going to sell because you expect the decreasing trend to continue. You have value investing, in which people say, oh, this stock has a given value. The Bitcoin is worth $50K. So if the Bitcoin is higher than 50K, it means that it is overpriced and I'm going to sell it. If the Bitcoin is below 50K, it means that it is underpriced. It's worth more than it was that is currently exchanged for, so I'm going to buy it. You also have nose traders, which people will assume will behave completely randomly, I like crazy persons, but you have many different strategies. And in some sense, you can just see it like a game. This is a game, and this is the different strategies. This is the meta of the humans. This is the human knowledge about this game. This is the human knowledge about financial markets. So what would happen if you let these evolution-driven algorithms play this game? Would they reinvent these strategies that are well known by traders, by practitioners? Would they even something new? Would they even find some new strategies, some new correlations? Would they find some hidden undervalued assets? And we are all in this cryptocurrency bubble at this stage, and one can only wonder what would happen if you trained some AI programs, some evolutionary algorithms to analyze all these data, analyze these patterns, and coming up with different, completely autonomous, completely own individual strategies for how to trade. And this is really what this project is about. The key is that you could use for so many things. The first thing is theoretical. You could, if you have a good model for the evolution of financial strategies, you can incorporate this evolution into all the models we have on financial stability, the crisis, the bubbles. All these models really struggle with the learning part, obviously, because learning is open-ended. It's not just tuning a parameter. It's not just looking 1 month before, 1 month after. You can create something completely new out of your strategies. And this method, these GAs that are so good at exploring very high-dimensional spaces, they can be the tool that can capture the open-ended or achieve the very large nature of this evolution, this learning. You have also, obviously, operational applications. And I think the prediction company was one of the first automated trading companies back in the 80s that was using some GAs, some complete trading bots that were completely learning on their own. And another idea is that if you make a parallel between this evolution, this financial system, and the adversarial attacks, you could actually try to let evolution find some loopholes in the current regulations. We have all this financial regulation, and we test it with our stress test model, with other models. And these GAs that are so good at creating innovative solutions, that are looking for novelty, that are good at finding things in very large dimensional spaces, they could actually be the tool to attack the functional regulation, to see what are the weaknesses, what is the functional regulation missing, or what scenarios are not being considered. And this is really a way in which these methods could really challenge our current understanding of regulation, of everything we understand about the financial system. There is also a very nice path of these projects towards very different grounds in artificial life and open-endedness, which is that if you have an artificial stock market in which strategies are evolving and these strategies are shaping the market, basically the evolution is going to determine the price of everything, you have really something completely autonomous. You have a self-creation of new niches, of new environments, of new challenges, and also of new solutions at the same time. So you really achieve a system that is constantly displaying novelty, constantly inventing new things, constantly being creative. So this is not done yet. This is actually a very long-standing problem, that how can we generate open-endedness? But I think this project carries a sort of unique perspective and maybe a way to achieve that. And moreover, a way to obtain maybe new insights about the financial markets, to make it more stable, to make it more efficient, to understand better regulation, to propose better regulation to avoid crisis, but also operational applications if one wants to make money. There are so many things that you could do about GAs. One of the recent things I was doing just this morning was to try to model the coevolution of the various strains of COVID and the policy measures. And you can really simulate this kind of arms race into GAs. And this is only one of the many things that are possible. And I would say the only limit is the imagination. So I've talked about hybrid GAs, so combinations like the NEAT algorithm, in which you mix evolution with deep neural networks or reinforcement learning. This is evolutionary reinforcement learning and neuroevolution. Basically, you can really combine these methods. They have some very good qualities, each on their own, and by combining them, you can really expand what these methods are capable of doing. And you can obtain these kind of neural networks, for example, with optimal architecture, with different ways to determine how to build them. An immense possible perspective, and I think I watched with great interest the previous talk in this series with quantum computers, quantum computing, quantum optimization, and a great possible future for GA is actually quantum genetic algorithms. And you have people have been talking about this for quite some time now, but maybe now you can actually see it coming. The idea would be, if you retake our binary string of 0 and 1s, we are quite efficient with the GA at scanning very large spaces, so many different elements. But each gene, each element of the vector is still either 0 or 1. And if you shift to the quantum paradigm, you can have some very unprecedented such parallelism. And I would really be surprised to see the speed at which quantum genetic algorithms could be solving these problems by considering many things at the same time. One important future perspective that I wanted to outline as well is that in everything that I described, the fitness function was extremely prevalent. We wanted a measure of how close are we to our progress. We wanted a measure like a real-world function or loss function in deep learning. But what if we get rid of the fitness function? What if we have non-objective search, non-objective evolution? And the key thing is that nature doesn't have an objective, and nature created all these things. It created ourselves, our intelligence, even quantum computers by extension, without an objective. And in this extremely insightful book, Stanley and John Lemon, Why Greatness Cannot Be Planned, they really try to show how following the objective can sometimes lead to deception, to how following the objective gradient will actually not get you to the objective itself, and how looking for novelty, looking for other things, looking for stepping stones or for promising developments can actually make you closer to the objective than just following blindly the objective. And an example of that is actually that if you try to solve this problem, you are at the point green, you have a maze and you want to get to the red dot. If you just look at the objective gradient, so you just look at the distance between yourself and the objective, you would just naturally go up, 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 and going to face a wall. Okay, this is not the good one. Maybe you try this one. This is still making you closer to your objective. But here, to be closer to your objective at this bifurcation, you will need to go and hit your head on the wall. And to actually get to the objective, you would need to get further away from the objective many times. And this is really an example in which if you're too focused on the objective, if you're so head down into your fitness function, you may just miss the real solution to your problem. And there are many situations in which this novelty search, this algorithm that will not try to maximize the objective gradient, but that will instead try to be looking at novel ways, novel solutions, can be outperforming objective search. There are also different things. The idea is that you could let GAs evolve their own parameters. Not only they are evolving a solution, they could be evolving themselves. There is some work that is done to try to pick up some key biological facts, what makes evolution strong, what makes evolution efficient, what makes life on Earth complex and adaptive. And there is a lot of work trying to understand these key ingredients in order to put them in our algorithms to be able to design not only the continuing solutions, but maybe more complex objects, digital organisms, financial strategies. And this has a lot of connections with artificial life and general AI. So to go forward and to wrap up, I hope to have conveyed the message that GAs have very desirable qualities, that we have now new ways to overcome their limitations and new perspectives and immense possible applications that sound very promising. I would add that it's really a widely applicable technique. There is a wide potential for interdisciplinary. It is already used in a lot of fields. You have some nice combinations that are starting to emerge. It can give some different insights that what our current algorithms can give. And I would really emphasize that it's really accessible. It's really not hard to code a GA, and you actually have a lot of resources online to get started with your own digital evolution. Maybe you have a different specific problem you want to solve. Maybe it's just about your supermarket list, or maybe it's about your optimal neural network, or maybe it's about something else. And in each of these things, GAs can give you maybe an unexpected but interesting solution. So to wrap up, I would have really to thank you all for your attention. I would welcome any question you have. And if you want to follow up on this, you are most welcome to contact me at my email. So at maths.ox.ac.uk. And just to finish, this is just a list of different, if you're really interested and you want to hear more about it, this is a list of key references. And the ones that I would recommend you is this book. No, not this one. This one is great, but this one from Wiransky, Hands-on Genetic Algorithms with Python at PAT. This is really an extremely nice introduction. You have all the codes. The codes are explained, they work. It's super nice. This is my review. This is the key paper from Stanley on how you can use evolution to really improve your neural networks. This is the Python workbook associated with it. And if you want a general introduction on genetic algorithms, you can read a very short paper from one of the creators of GA, John Holland, Genetic Algorithms, Scientific American. So yeah, thank you so much.
Thank you, Aymeric. Very, very interesting talk, and learned a lot about genetic algorithms, and you have a great communication style, so you were able to make all the concepts relatable. Perhaps in the interest of time, we'll go to 2 quick questions. There's a number of questions and comments in the chat, but just to be respectful of everybody's time. There's an interesting question here, which I'm putting on the screen. So what if your fitness function is state dependent? And would you recommend that, for example, perhaps if the fitness function changes over time, that you then have different GA searches going on, or how would you handle the state-dependent fitness functions?
Well, it's a very good question, because we have been really talking about static problems, problems that don't change. And it's been really a struggle to try to apply these GAs to dynamic environments. The problem is that you need to be extremely efficient in your evolution, because if you take ages to find the solution to your problem, the solution may be irrelevant if the problem or the state has changed. One way I've seen it being done to handle dynamic environments is to have some operator called hypermutation. It's not just you are going to switch some elements in your DNA sequence of the individuals, is that you're going to kill a given proportion of these individuals in population and replace them with random new solutions. This is a way by which you can have a continuous level of search that maybe allows you to be more adaptive facing dynamic environments or different states.
Okay, thank you, Aymeric. Maybe we do one more question here, and there's a lot of very interesting questions, but I think this one relates directly to your search, and this one has to do with, do you use ontologies and graph data underneath the structure for your emerging knowledge? So your research on learning, when you're using GAs to represent knowledge as a function, as you talked about, two agents potentially communicating, and you're considering that as a part of the process, are you using some form of an ontology or a graph structure to represent the entities and their relationships?
I am not currently doing that, but this is an extremely fascinating approach. And in fact, indeed, if you just take a dive at social learning and social interactions, these things don't happen in lattice, right? You are all embedded in small world networks, and you have a lot of work that's been done in network science to tackle that. So what would be really exciting would be for GAs to develop their own social networks. I believe this is doable if you give them the ability to select who they're going to mate with, who they're going to meet. I think this is doable. This is one more layer of complexity. And I think this will be adding a lot of realism on the social learning dynamics and to make this happen. So thanks a lot for the comment. It's a really interesting direction.
Absolutely. Thank you, Aymeric. And one last question, which I think is quick to sneak in, is can we get these slides? So if you can email them to me, Aymeric, I can put them in the description for the YouTube video. That'll be great. But thank you, Aymeric, and we'd love to have you back in a couple of months to get an update on your journey, especially the very interesting work you touched on, where you're modeling the evolution of the mutation of the COVID virus and the evolution or the mutation of the policies, the evolution of the policies that policymakers are making to combat the virus. We'd love to see how those multi-agent arms races pan out. But thank you so much for your time. Appreciate it, Aymeric, and hope to see you very soon. Bye for now.
Same.